Good afternoon. My name is Marek Michalewicz. I'm the director of Interdisciplinary Center for Mathematical and Computational Modeling, University of Warsaw. And it's my great pleasure to welcome you all for the fourth in a new series of virtual ICM seminars in computer and computational science. We've started this series following immediately after our March 6th edition of Supercomputing Frontiers Europe conference. Since we are now almost everywhere confined to isolation, to working from homes, restrained from moving around, from travel, from visits, and face-to-face meetings, this format of getting together and sharing information, news, delivering seminars and lectures became a new norm. And today I have a very special pleasure of welcoming a speaker from the University of Melbourne, from Australia. I feel very strong bond with Melbourne. That's perhaps the city I lived for the longest in my life, except of Wrocław. And we have the pleasure of welcoming Dr. Simon Mutch, who is a postdoctoral research fellow at the Australian Research Council Centre of Excellence for All-Sky Astrophysics in 3 dimensions, Astro 3D. He's also a research data specialist in the Melbourne Data Analytics Platform, MDAP, based at the University of Melbourne. Dr. Mutch received a master's degree in physics from the University of Edinburgh and was awarded his PhD in astrophysics from Swinburne University of Technology, Australia, in 2013. His astronomy research is focused on the first galaxies and their impact on the evolution of the universe, which he studies using a combination of supercomputer simulations and theoretical modeling. Through his role with MDAP, he's also currently collaborating with academics in areas such as climate science and ecology to help uplift their digital research capabilities. Dr. Mutch contributes to the Australian astronomical community through a number of national committees and is an inaugural Science and Technology Australia STEM ambassador, a position which sees him meet with policy and decision makers to advocate for the importance of STEM and related fields. Before we give the floor to Dr. Mutch, let me just acknowledge our sponsors. Our series of seminars is sponsored by Dynami, HPC Enterprise AI, and Tabor Communications. And I wish to invite all of you who are here, and also I ask you to spread the word about the following seminar next week, which will be delivered by Dr. Catherine McGouch from D-Wave Systems. Professor McGouch spent 30 years in Amherst College. He's well known in the era of algorithms and computational complexity, and in many recent years, since 2013 or 12, has been very active in doing research on computational complexity and benchmarking of quantum annealing systems. So that will be a very interesting talk. I invite all of you. After that, on the 21st of May, we will welcome our own ICM scientist, Dr. Franciszek Rakowski, who is a leader of ICM group, which develops a model for the distribution and the progression of COVID-19 epidemic in Poland. That's a unique model based on agent systems with the extreme level of granularity and detail, unmatched, in my my best knowledge, and you'll certainly learn very interesting details about this work at ICM in the group led by Dr. Rakowski. And I can assure that we have a very interesting schedule going right up to end of June. So please stick to this series of seminars, spread the word, and I welcome you all. And now let me leave the space to Dr. Simon Mutch, whom I welcome warmly in Poland and in virtual space. And of course, I welcome all of you from all over the place. I can see a long list of people, and I know some. I don't know many, but I'm very pleased that you are all here. So welcome, and it's over to you, Simon. Thank you.
Great. Thanks very much, Marek, for the kind introduction and for the offer to come and present this seminar today. I really appreciate it. So as you've heard, today I'm going to be talking about HPC simulations of the early universe. And this is work I've been carrying out as a postdoc at the University of Melbourne, part of the Astro 3D Centre of Excellence. If I've got time at the end of the presentation, though, I'd also like to touch on how this ties into the other role I hold at Melbourne University, which is a senior research data specialist with the Melbourne Data Analytics platform. And also, before I begin, I'd like to say that I think there'll be opportunity for questions at the end, if I understand right. But if anything isn't clear to you and you're interested, please don't hesitate to drop me an email as well. I'm always happy to answer email queries. Okay, so I'd just like to begin by doing a little bit of a overview and motivation of what exactly I mean when I say the early universe. So immediately after the Big Bang, the universe was filled mostly just with neutral hydrogen. There wasn't really much else there. But then there were gravitational perturbations that caused gas to collapse in on itself, and eventually stars and galaxies began to form. And those stars gave out light, which was of high enough energy to start to ionize the surrounding neutral gas. So it stripped electrons off that neutral gas and changed its properties. So that's the process you can see in this diagram here. So we have the Big Bang at early times, and then the first stars and galaxies start to form, and the ionizing photons from these galaxies cause these ionizing bubbles to form, where they've ionized the surrounding neutral hydrogen. Then as you get more and more galaxies, and the galaxies get larger, those bubbles start to overlap until eventually the entire universe became reionized sometime around 12.5 billion years ago. So we're really only here talking about the kind of first billion years or so of the universe's history. And this is called the epoch of reionization. So one of the really nice things about ionization is that the neutral hydrogen actually emits radiation at a particular frequency at 21 centimeter, which is in the microwave. But then due to the expansion of the universe, that gets moved into radio frequencies here on Earth. And so detecting these radio frequencies is actually a big international effort. And there's lots of large-scale international collaborations ongoing at the moment. So I've just listed a few here, such as HERA, the Murchison Wide Field Array, which is in Western Australia, is the one I'm most familiar with. And all of these are building up to the Square Kilometre Array, which I'm sure some of you will have heard of. And that's going to be built both in South Africa, and the low frequency component that's going to be looking at reionization is going to be in Western Australia as well. So what makes studying reionization interesting? The reason is because this kind of bubble structure that we see is sensitive to the physics of galaxy formation. And so that's really interesting, because what it means is that if we can observe this reionization signal from the 21 centimeter emission from neutral hydrogen, then we can infer something about the galaxies which are driving this process, this reionization process. But what's even more interesting is that the reionization signal is sensitive to all galaxies, not just the very brightest galaxies which we can see at these early times. So what this plot here is showing is called the luminosity function of galaxies. And so basically what it is on the x-axis is the brightness of galaxies in weird units that we use in astronomy called magnitudes. So it kind of goes reverse to what you would expect. Bright galaxies are over here, faint galaxies are over here. And this is the number density on a logarithmic scale. And so what you see is that the number of galaxies is actually dominated by the very faint ends. But we can't actually see the very faintest galaxies. These shaded regions here show the uncertainties from observations. And once you get to galaxies around about -15, the uncertainties really blow up, because we can't really see those galaxies. They're just too faint and too far away. But they're all producing light. And so that light is interacting with the surrounding neutral hydrogen and causing it to be ionized. And so by studying this reionization structure, we can also learn something about the very smallest, very faintest galaxies that we can't actually see. So to give a bit of an analogy, the one I commonly like to use is the idea that you have a whole pile of stones and gravel in your hand. It's made up of lots of different types of stone, which you don't know. They're all different sizes. And then you drop those stones into some water. And by looking at the ripples, you want to try and understand what the properties, what the distributions of properties were of those stones that you just dropped into the water. So that's the general idea here. That's what we want to be able to do by looking at reionization. Okay, so that was quite kind of physics and astronomy heavy, but I just wanted to give you that kind of overview of what I mean by reionization and the early universe and why it's particularly important. So the main problem, though, is how do we connect the properties of galaxies to the signature of the bubbles that we would see during reionization? What we want to know is, for example, if we see very many large bubbles, does that tell us something about how efficient star formation is in galaxies? Or perhaps we see very few bubbles, and so we want to understand that as well. So obviously we can't wind back the clock and change the physics of galaxy formation and observe a whole new universe. So we need some way to connect the properties of galaxies to the reionization signal. And so for that, we use cosmological simulations. So the idea here is that we take all of our best knowledge about how things work, and then we try to simulate all of the complicated physics that goes into galaxy formation and evolution as self-consistently as possible. So the background here is a movie of the evolution of a cosmological hydrodynamic simulation from the illustrious suite of simulations. So this is actually reasonably old now, and it was run back in 2013 in several different facilities across Europe. But what the movie is showing you is a patch of the simulated universe evolving with time, and it's changing through looking at the temperature of the gas, which we saw right at the beginning, and then we were seeing, if I can start that again, yeah, so this is us looking at the temperature of the gas. Then it moves on to looking at the distribution of metals in the gas. And finally, we see the distribution of mass and matter. So these simulations are incredibly powerful, but they involve lots of different bits of physics that go into them. So we need to consider things like gravity and dark matter. Also, there's heating and cooling. There's lots of turbulence and supersonic shocks happening. and we need to consider the chemistry of the gas, how stars form, how they evolve with time, what happens when they die. So they typically produce supernova, which inject large amounts of energy back into the interstellar medium, and also black hole growth and that feedback effect on the evolution of galaxies as well. And some simulations also include things such as magnetic fields and full radiative transfer to explore what the properties are of the light that's coming from the galaxies. And on top of that, we have many different methods that are commonly used for these simulations. So smooth particle hydrodynamics, adaptive mesh refinement, and moving mesh codes are all reasonably common now in terms of modern simulations. So as I say, while these are incredibly powerful, they are extremely computationally intensive. And that's because there's a large dynamic range, both in terms of temporal and spatial resolution. And as I said before, there's lots of shocks and lots of highly turbulent gas. So just to give you some examples, here's just two recent recent simulations, which I just kind of randomly picked out of the literature from recent years. So we have the illustrious TNG simulation. So that's literally the next generation illustrious simulation, which you just saw the movie of. And this evolved a box which was 1 billion light years on a side on the Hazelhen supercomputer in Stuttgart. And that took 24,000 cores and roughly 35 million CPU hours. Similarly, the Blue Tide simulation, which was run in the US, is a bigger box, but it took 81,000 cores with about 8 threads each and about 20 million CPU hours, running on the Blue Water supercomputer, taking up pretty much the whole machine there. So these are really computationally expensive simulations. And what we're always doing is we're making this trade-off between the amount of resolution we get in the simulation and the size of the simulation as well. So we either have to make the choice, do we want to resolve things very well, but restrict ourselves to a small volume, or do we want to go to large volume so we can get a statistically significant sample of galaxies and look at the statistics of the galaxy populations? But then to do that, we need to give up some of that mass resolution. And so we can't model things as accurately. And so this problem is particularly acute, though, if we want to start talking about the early universe and reionization. So the reason for that is because if we think back again to that picture of those ionized bubbles surrounding galaxies, they can be really large. So towards the kind of mid to late stages of reionization, those bubbles are typically tens of millions of light years across. And so if we want to simulate this, we need to simulate a large enough volume that we can get many of these bubbles so we can look at the statistics. But then we also need to look at simulating the galaxies which are producing the ionizing photons that are going into the interstellar medium and producing ionized bubbles. And we want to learn something about those galaxies. So we need to be able to model the physics going on in the galaxies as well that's producing the light. So in particular, things such as star formation and supernova feedback. So when stars die and they give out large amounts of energy. And so just to make things even more difficult, these simulations have a lot of what's called subgrid models in them. So just because our computing power is limited and because there's such a large dynamic range involved, we can't fully resolve all of the different bits and pieces of physics going on. So for example, we need to put in analytic models or phenomenological models to describe things such as gas phases, things such as the chemistry of stars and supernova explosions. Or for example, we might need to introduce a density threshold above which stars are allowed to form. And that would happen typically with some free efficiency parameter that's calibrated to allow us to reproduce observations of the universe. And so that's what I'm showing on the right-hand side here. This is a plot taken from a paper looking at another suite of simulations called the Eagle simulations. And what they've done here is they've varied some of the free parameters in these subgrid models, which is shown by the different lines here, to try and reproduce observations of the real universe, which are shown by the by all the different points here. And what this is actually showing is the total stellar mass density, so the total amount of mass in the universe in terms of stars as a function of volume, and then all of that as a function of time. And you can see that their fiducial model manages to reproduce the observations, but they had to play with the parameters in order to achieve that. And the problem is that as we go further back in time and we look at the very early universe, things get very faint, they're very distant, they're very small. And so our knowledge about the early universe is not nearly as good as our knowledge about the nearby universe. And so there's very little constraint on these free parameters. So ideally, what we'd like to be able to do is to run many, many different realizations of the simulations, to test different star formations efficiencies, different chemistry models, different feedback processes, and to see how that changes the structure of the ionized bubbles, so that when we measure the ionized bubbles, we can infer something about the galaxies. Fortunately, though, the makeup of the universe gives us a little bit of a helping hand here. So I'm sure many of you will have seen this kind of diagram before, which shows you the energy density makeup of the universe. And what you find is that the vast majority, about 70% of the universe, is made up of this dark energy, which is kind of pushing everything apart. Then we have around about 25% is made up of dark matter. So that's this kind of invisible material that makes up the majority of the mass of the universe. And then only a very small fraction, this kind of 5% or so, is what we would consider normal matter, all the things we see round about us and interact with in our daily lives. So what this actually means is that we can do a pretty good job of simulating the position and the large-scale distribution of matter by simply ignoring normal matter. And that makes things much easier, because that means we no longer need to worry about things like gas and shocks and star formation and things like that. All we care about is getting the large-scale distribution of matter correct. And so to show this kind of pictorially, this is a slice through a large-scale simulation that considers only dark matter. So what we do here is we take all the matter in the universe and we pretend that it's completely collisionless. And so this is a body simulation. There's only gravity and no other forces. And what we can do is we can pour all our computing power into just doing this problem of gravity, essentially, and doing as big a simulation to as high resolution as we possibly can. Then what we do is we go through the simulation and we identify all these little knots, which I've highlighted just a few of here. So these are called dark matter halos. These are conglomerations, clumps of dark matter. And these are the sites where we know that galaxies form. So those dark matter clumps provide a potential well which attracts normal matter into it. It just falls in through gravity, and then that's where stars and galaxies start to form. So if we identify these dark matter halos, then what we can do is we can track them throughout the life of the simulation and build up these accurate hierarchical merger trees of how these halos form by merging with each other over time to form larger and larger structures. And what we do is we then take these merger trees and we feed them as input to another kind of model called a semi-analytic galaxy formation model. And this is actually the type of simulation type of model which I've spent the majority of my research career working with. So what we basically do is we take these hierarchical merger trees as input, and then we effectively paint on galaxies using a series of analytic approximations, but all physics-based, all based in real things such as cooling, heating, star formation, supernova feedback, all those kind of processes I've already mentioned. So what you see in this little movie here on the right-hand side is an example of one of those dark matter halos that you'd get from a simulation. And then this is just showing kind of pictorially the kind of galaxies which would end up being placed in here. And so you can see as you rotate around, this is showing you the galaxies you get in this dark matter halo. And then eventually the movie changes to show you how the dark matter builds up through merging. And similarly, we're able to populate those halos with galaxies. So the kind of painting on of the galaxies is actually a reasonably computationally cheap process. And instead, we pour all of the computational resources into doing these large n-body simulations because we only need to do them once. And so this is a large and very established field in astronomy. It's been going for a long time now, and we've really managed to, I think, do a good job of making this as efficient as we can using current architectures. So direct n-bodies, so just doing the gravitational force between pairs of particles across all particles in the simulation is just way too expensive. So that scales as n squared. So instead, commonly what happens now is that we use a mixture of hierarchical methods to do the gravity calculation. So these vary from tree-based methods on small scales, where we break the simulation volume up into different size boxes depending on how far away they are from the particle of interest, and we can approximate the gravitational force by just considering these boxes instead of the individual particles, essentially. And the other method, which is commonly used on larger scales, is to place all of the particles onto one of these meshes with different refinement levels, and then to Fourier transform that and efficiently work out what the forces are on large scales that way. And then we also need to add things such as softening on very small scales so that we don't get singularities when particles get too close together. And also things such as dynamical time steps for different particles depending on the accelerations which those particles are experiencing. So in very dense regions, the particles are moving very quickly relative to each other. And so you need to have resolve that motion. Whereas if the particles are very spread out, their accelerations tend to be a lot lower, and so we can have larger timescales for those particles. And so just as we saw with the full hydrodynamic simulations, n-body simulations suffer from the same kind of problems, though, that we're often trying to make this trade-off between the resolution of the simulation and the amount of volume that we can simulate. So this plot here is just showing how the kind of total particle number in these n-body simulations has evolved as a function of time, so the years of the simulation. And you can see that we're rapidly managing to increase the particle numbers, taking advantage of GPUs and alternative architectures, and getting more efficient and better at doing our data management and data flow. But still, we're having that problem that we basically still need to make the decision between, do we want very high mass resolution, be able to resolve very small structures, or do we want to be able to resolve many, many structures in the large box? Okay, so I've talked about hydrodynamic simulations and how computationally expensive they are. And then I've talked about how one effective alternative for large cosmological volumes is to do these kind of collisionless n-body simulations. And then to couple this to a semi-analytic galaxy formation model. But how do we actually go about doing all this in practice and then connect it to the epoch of reionization and that bubble structure that I keep talking about? So as an example, what I'm going to use here is work that we've done at the University of Melbourne as part of the DRAGONS program, which stands for the Dark Ages Reionization and Galaxy Observables from Numerical Simulations. We love our acronyms in astronomy. Everything needs to have a good acronym. And so as part of the DRAGONS program, which was led by Professor Stuart Wythe at the University of Melbourne, we ran our own in-body simulation. It was by no means the largest or highest resolution by international standards, but it was, we constructed it and designed it to be perfect for this study of reionization. And so this is just a slice through the simulation at early times in the universe, sorry. I should also say at this point, if I talk about redshift, that's me falling into kind of astronomer lingo. What I'm really talking about is time there. So high redshift is early in the universe, and low redshift is closer to the present day. Just in case I accidentally do that, I will try to stick to the age of the universe though, whenever I catch myself. And so, yes, this is showing a slice through the simulation very early in the simulation, and it covers approximately 300 million light years on the side. And each of these particles in the simulation corresponds to a mass of about 4 million times the mass of the sun. So it sounds like a lot, but you know, we have billions of these particles in here, and we're doing an extremely large volume. So this actually is quite high resolution. So then what we did is we went through the simulation, we identified all of the dark matter halos and built up those hierarchical merger trees that I talked about before. And then we fed them into our new custom semi-analytic model that we developed specifically for looking at high redshift. And using that model, we can populate the volume with a statistically realistic sample of galaxies. But then what we also do, which was unique at the time with the DRAGONS program, is that we use the information of these galaxies to calculate how many ionizing photons they were producing, and then fed that into another code called a semi-numerical model that then was able to give us what the ionization state of the volume was as a function of position. So basically, it allowed us to figure out where these ionized bubbles were. Is the largest of these dots here, and you get large individual bubbles, and around these clumps of galaxies, you get smaller bubbles which all overlap though to form one big ionized region. And so what we do is we calculate the properties of the galaxies, and then we run our semi-numerical model to get the properties of reionization in the volume. And then we evolve our galaxies, and then we run the semi-numerical model again to get the ionization state, and we just keep doing that in lockstep. And then this is what you end up with. So at very early times, you get some star formation, and you can see the first ionized region starting to form, but then you actually get feedback which stops those galaxies being to continue to grow. But then eventually over time, more and more of the matter in the universe starts to collapse into these halos, and the feedback isn't efficient at stopping that happening anymore. And all of the bubbles start to get larger and overlap, and eventually you end up with a fully reionized universe. So, as I've said, but I just kind of want to reinforce here, what this methodology allows us to do is to run one really expensive n-body simulation on the order of millions of, or tens or hundreds of millions of CPU hours, and then to just do that once. And then we can keep running our semi-analytic model over the top of that. And we can calibrate the free parameters of that model to allow us to reproduce key observables in the universe, in the real universe. And so this is just another example of that. Here I'm showing the luminosity function of galaxies again, this time just to be difficult. The bright galaxies are on this side, the faint galaxies are on this side. The observations are shown by the blue points, and the prediction from our model, after we've calibrated the model to be able to reproduce this and other observations in the universe, is the black line here. So we can do a good job of reproducing these observations, which is great. But running the semi-analytic model only takes, on the order of 10 CPU hours. And so that's where things start to get really powerful, because what that means is that we're no longer restricted to running one really big cosmological hydrodynamic simulation once every few years and needing a large grant and a whole supercomputer to do it. Instead, we can start to explore what happens when we change different parameters in our galaxy model, and we can then see how that changes the signal from reionization. So on the left-hand side here, this is another plot from our semi-analytic model. This time I'm showing the number density of galaxies as a function of their stellar mass. And the observations, again, are shown as points here. Our model is shown by the blue line here, and then all of these other lines show what happens when we turn on and off different feedback processes, when we play with the efficiencies, and really just play with all the dials and see what happens. And then what we can do, and what I'm showing on the right here, is translate that into future observations of the 21 centimeter signal from reionization. So this is showing the power spectrum, which basically shows the amount of signal you get as a function of different spatial scale. And so you can see, as we use these different physical models, it has an impact on the structure of the reionization signal. And we can start to use this not only to try and back out when we measure the signal, what does it mean for the galaxies, but we can also do things like just look at where we're most sensitive, and that helps plan future experiments, so we can build our telescopes in order to have the best chance of being able to detect the largest variations in the signal. And in fact, when the models are so computationally cheap, what we can also do is we can run them tens of thousands of times, hundreds of thousands, to do full statistical exploration of the parameter space and really constrain unknowns in galaxy formation physics statistically. And so, I'm not going to go through any of the details of this plot, but it's basically what's showing here is running our semi-analytic model through an MCMC process, so a Markov chain, a Monte Carlo Markov chain process. And this is the two-dimensional posterior, showing the likelihood of different parameters given the set of constraining observations we use. And so you can see you can start to put constraints on different parameters. Here, the star formation efficiency, these two ones have to do with supernova feedback, and so on. So that's what I guess I wanted to cover in terms of the tools and techniques that we use to study the early universe. And now I just kind of wanted to talk a bit about the actual simulations that we're doing now as part of the Astro 3D Centre of Excellence. So Astro 3D is a 7-year, $40 million Australian dollar research centre of excellence funded by the Australian government. And so it's supported by at least 6 collaborating Australian universities, 3 national and 7 international partners. And it covers a broad range of science in astronomy and astrophysics that basically comes under 2 themes. One is the origin of matter and the periodic table, and the other is the origin of the ionized universe, which is what I've talked about through the beginning of this seminar. But then underpinning all of this are these 2 threads that kind of cut across everything. One is our data-intensive astronomy program, and the other are the Genesis theoretical simulations, which are the next generation of simulations that we're doing in Australia to try and support Astro 3D science. So as I've said, the science goals of Astro 3D are really broad. So as part of the centre, we have people looking at things such as galactic archaeology. So that's where they take spectra of hundreds of thousands of stars in our Milky Way galaxy and then attempt to try and understand how the galaxy formed by looking at different clumps of similar stars and looking at their properties to try and understand when did these stars fall in, when did these ones form, and do archaeology in that sense. Then we also have other surveys which are producing huge amounts of spatially decomposed spectra of galaxies, in particular the SAMI Galaxy Survey. Then we have the Murchison Wide Field Array, which is looking at the epoch of reionization and trying to detect that 21 centimeter signal. And we also have people working with the Hubble Space Telescope, looking at some of the early galaxies in the universe directly using space-based telescopes as well. So it's a really wide range of science. It covers the nearby universe, our own galaxy, all the way back to the very first galaxies in the universe. And so the role of the Genesis simulations is to try and support all of that science. And what that means is we've had to take quite a varied approach. And so what we've done is we've combined a suite of large body simulations, but also zoom-in simulations with full hydrodynamics of individual galaxies, where we can test different physical prescriptions, different kinds of star formation, supernova prescriptions, and see really in detail how that changes the properties of individual galaxies. And that's really important for things such as the galactic archaeology, but also we can take what we learn from those very detailed zoom-in hydro simulations and use that to inform the physics that we put into our semi-analytic models as well. So Genesis is made up of a team of around about 30 researchers spread across institutions, and we have really close collaborative links with researchers in Europe and places like Leiden and Max Planck Institute for Astrophysics, and also in North America. And so in terms of our n-body simulations, as I say, we've been running a suite of those. And the reason that we're running more than just one is, again, because of that broad range of science that we're interested in. And so for the for the early universe, we want to be able to resolve all of the small structures that we can, because we need to be able to capture all of the galaxies producing the ionizing photons. But we also need to be able to go to very large box sizes to capture those and the statistics of those bubbles. And so what that means is typically we try and pour all our computational resources only into running those simulations until round about the end of reionization. Whereas we have lots of other physics that goes all the way down to the local universe. And so we're also running other n-body simulations with different box sizes, different mass resolutions, which are tailored to answer different physics questions. So these are just 3 of the main n-body simulations that we're running as part of Genesis. But really, what we're gearing up for is to run one big box, which is 500 million light years on the side, with 8,000 cube particles in it. And so one of the quotes from the Astro 3D report is that this is groundbreaking scientifically and computationally challenging. So this is going to be one of these simulations which is actually competitive on an international scale. And so there are a number of things which are allowing us to pursue such a large n-body simulation in Australia. So one of those is that we now have access to the latest supercomputer at the National Computing Infrastructure in Canberra in Australia. So NCI is one of the 2 national facilities we have. So this one, as I say, is in Canberra, and then we also have POSI in Western Australia as well. But NCI has recently upgraded its system to a new one called Gardi, and it's not yet fully complete, but we'll eventually have 3,000 Cascade Lake nodes with 24 CPUs each and 192 gig of RAM. I won't go through all of the stats here, but this system is replacing a much older one which was installed in 2013. So it's really a big boost to the computing power that we have available within Australia. And through the Genesis simulations, we're actually in the fortunate position that we're helping NCI stress test the new machine. And we're doing that with our simulations because they're large enough scales to really take up a significant portion of the machine and allow us to basically try and break it. On top of that, we're also using the next generation of simulation codes. So in particular, what we're using for Genesis is a new code called Swift, which was developed at Durham University as a collaboration between the Institute for Computational Cosmology and the School of Engineering and Computer Science. So what makes Swift particularly interesting and particularly good for this kind of science is that typically in these simulation codes, the domain decomposition is done spatially. So we break the simulation up into individual contiguous volumes, and we spread those across the different nodes of the supercomputer to try and load balance the problem as best we can. However, because different parts of the universe are much denser than other parts, and that changes as a function of time, it can be quite difficult to get good load balancing and to keep the machine occupied the whole time and not just be transferring information between nodes. So what Swift does is it does away with that kind of idea of domain decomposition spatially and instead uses a task-based decomposition. And then it also has these all the bells and whistles that you would expect for a high-performance simulation code. So it's hybrid MPI with threads, and SMID intrinsic for all the gravity calculations and things like that. And so what we end up with is if you compare Swift to kind of one of the industry standard codes, it's getting a bit older there. There are newer versions of this code, but the same basic idea stands is that you can achieve speed ups on the order of 30 to 40 times by moving to this much more efficient task-based decomposition. And so what I think is really important to highlight here is that this new code and the efficiency of it came through a collaboration between professional computer scientists and astronomers. And it's really down to clever choice of algorithms that gives us significant performance improvement and is allowing us to go after such a a large simulation using computing resources we have available to us. And then just to kind of extend that idea as well, another thing that we're doing as part of Genesis is we're looking at ways that we can kind of cheat, essentially, and to do the best simulation we can, but then to augment that simulation with dark matter halos which are produced using theory. And so that can potentially allow us to get much higher spatial resolution for free, essentially. Now, obviously, this can't be as accurate as doing the real simulation, and so the question is, how accurate can we make that, and how close can we get it to a real simulation answer result? And this is something that's been worked on by one of our PhD students at the University of Melbourne, Yi Sheng. And so we're getting some really nice results at this stage, and so what this plot shows here is the solid lines are from real simulations. And so we have a very small volume, but very high resolution simulation here. And then we have a much larger volume and lower resolution simulation here. And this is showing the number density of halos as a function of their mass. So you can see for the low resolution one, we don't get any of the smallest structures here. And that's what we want to be able to try and get. And so what these dashed lines here are showing are the results of doing this extending of the merger trees using theoretical arguments. And you can see that we can actually extend the resolution of the simulation and get a very close result to the truth that you would get from a real simulation at very high resolution. But of course, we can do that in a much larger volume now. So that's a really promising avenue. And then I guess to finish though, I wanted to say that the future is getting really scarily data rich as well in terms of observations in astronomy. And that as a simulator is both really exciting because it means more data to compare against, but also it's a little bit terrifying in that our simulations are really going to need to keep pace with being able to make predictions and make comparisons with all this rich data that's coming off of next generation instruments. So for example, the square kilometre array, the low frequency component, which I think I mentioned before is being built in Western Australia, is going to have really quite terrifying data rates. So there's one statistic down the bottom here that I like to talk about, which is that the raw data coming off the telescope is going to be equivalent to about 5 times the estimated global internet traffic in 2015. So huge amounts of data. And then on top of that, we've got lots of new telescopes being built at the moment as well. So one such as the, I can't actually read the writing on my laptop because it's so small, but I think this is the extremely large telescope, the ELT here. And so this is going to be one of the, a small number of the next generation really massive telescopes. And just to give you a kind of visual impression of what I mean by massive, this is the size of the mirror of the ELT compared to a human to scale down here. So these are huge telescopes that are going to be collecting lots and lots of light and getting lots and lots of really detailed observations for us to compare against with our simulations. With this huge amount of data, how we're going to store it, how we're going to process it, how we're going to convert it into something that we can compare with theory is something that I'm really interested in. And I think I've hopefully got just a few minutes left to talk about how that ties into the other role that I hold at Melbourne University, which is a data specialist in the Melbourne Data Analytics platform. So this is the kind of problems that we're thinking about in MDAP. So we're a team of academic specialists who are working to enable data-intensive research across all different disciplines at the University of Melbourne. So that includes humanities, medicine, social sciences, and then also STEM as well, so science, technology, engineering, and maths. And so MDAP was formed as part of a larger Petascale campus initiative at the University of Melbourne, which was a 5-year plan to accelerate the university's capacity for data-intensive research between 2018 and 2022. So as part of MDAP, we're really looking to do something which is a little bit different, at least to other universities in Australia, which is to have this model where we go out and we work with researchers, not as a professional service, but as academic collaborators. So we're academic specialists. We have all the same KPIs as normal academics in terms of contribution to research and papers and things like that. And so we want to be able to contribute and provide intellectual input into research and into how we can manage large amounts of data and efficiently process it. So these are the kind of 3 main things that we cover in MDAP. So I've talked a little about research impact, about computing, about helping to uplift the compute capabilities of researchers, particularly in domains where perhaps there's not such a strong history of really making use of high performance computing and other resources. And like I say, we want to collaborate with the researchers. We don't just want to be a service for them, we want to provide intellectual input. And so we have now a team of 20 specialists, and we come from a really wide range of backgrounds. We have people who have been hired internally from the university, as well as external hires. We cover all of the different domains, and we have really widely varying backgrounds as well. And what we're trying to do is we're trying to bring together multiple different computational disciplines, different organizational skill sets, and different domain knowledge as well. And one of the really key things that we're doing is we're not just focusing on kind of on very technical skills, on actually doing coding and things like that, but we're also really focused on this kind of data management aspect, on how we can work with people to ensure that they're keeping their data safely, they're doing all the best practices, they're thinking about ethics where appropriate, and things like that as well. And so we have a data stewardship team as part of MDAP, which are heavily involved in that. And so I think that was everything. I guess just to kind of recap the main points of what I've talked about today, I hope it's been interesting. So I've talked a bit about the early universe, and in particular the epoch of reionization. And hopefully I've kind of shown you a little bit of a taste of why it's so interesting and how it gives us this amazing opportunity to learn about galaxy formation in galaxies beyond what we can actually directly see. Of course, we need simulations in order to maximize what we can learn from these observations. And also, I've talked about how, especially in the very early universe, there is a lot of unknowns. There's a lot of free parameters that we need to tune. And so we need to run a lot of simulations to really explore the different physics. And so in Astro 3D, we're doing the Genesis simulations, which is a suite of high performance simulations for studying not just the early universe, but all the way through to the present day. And then I've talked a little bit at the end about how, as we move into the era of next generation telescopes, we're going to need to be able to employ clever techniques to exploit available HPC sources and really think about managing our data efficiently and ways that we can compute that, we can compute that. And yeah, I think that's it. So thanks very much for your time.
Yes, so right now we have time for some questions.
We are waiting for questions. Simon, thank you very much for a great talk. wonderful overview of a very fascinating field of science, of many fields actually. In the meantime, while we are waiting for questions from the audience, maybe I will ask a few questions. The first one is about the initial conditions for your simulations. How do you achieve inhomogeneity, sort of granularity of matter in universe? Sort of, do you see that in a certain way, or is it do you start from homogeneous initial conditions, spatial distribution?
Yeah, so we use observations, cosmology observations, so using the cosmic microwave background and other observational probes like that to look at the distribution of matter on different scales. And then what we do is we seed the initial conditions, exactly like you said. We seed them with the correct inhomogeneity to allow us to reproduce the observed cosmological signal. So one of the common ones we use is a glass. So where we basically start off with a homogeneous distribution of particles, but then we perturb them in the correct way so as to give us the inhomogeneities that we know will allow us to reproduce the distribution of different structure sizes and masses that we see in the universe.
Okay, thank you. The second question I have is, could you comment on any activities to use special purpose architecture for n-body simulation and cosmology? I'm aware of things in Japan, GRAPE series of computers. Is this line of work still continuing anywhere in the world?
Yeah, I think so. So actually, GRAPE is the only ones that I am actually aware of as well on that side of things. So I'm not aware of any kind of recent alternative attempts at specific hardware for that. The big push at the moment is to move our codes over to being able to take advantage of GPUs basically at the moment. So the most recent ones in one of the plots I showed, I'm not sure if I can get back to it. Yeah, so this one here that shows the some of the most recent n-body simulations that have been run. So the most massive one here, the Euclid flagship, I think that was run with a code called PKD Grav 3, which its main feature is that it's been ported to efficiently use GPUs, and that's what's really allowed them to run such a large simulation.
Actually, Simon, I remember reading about the early uses of GPU cards, and that was actually done by astrophysicists. It was definitely not AI. Back in the early 2000s, several sort of very smart PhD and postdocs ported n-body or similar hydrodynamic codes in astrophysics to GPUs, and that was the very first demonstration of usefulness of GPUs in general purpose computing, to my best knowledge. I have also another question for you. I'm still waiting for, we have something, but before we get to the audience questions, let me sort of use my privileged position and I will ask the third question. And that is, during our conference in March, we had a lovely talk by Professor Yufeng Deng from Stony Brook University, completely different scientific context. That was MD stimulation of blood platelets in veins in the human body. And in that particular context, you also face a situation where you have of the order of 6 orders of magnitude spatial differences between feature size in the tiniest particulates and up to the size of the vein. And in order to tackle, to speed up calculations, they have used the artificial intelligence method to differentiate time steps for different time scales. There are a couple of papers, recent papers on that. I just wonder whether similar approaches were tried in your research context.
That's definitely not something that I have heard of being tried. I know that people are starting to investigate using neural networks and different machine learning approaches for generating the statistics of simulations, and in particular for generating things such as these merger trees that we use as input to our simulations. I've not heard of that though. Actually, that's really interesting. Yeah,
I'll be happy to share if you like. And
yeah, that would be really nice.
So, okay, we have questions now. Simon, do you see the chat pane here? Oliver is asking. I think Oliver's questions.
Yes, I do. Yep.
I'll leave it to you.
So question from Oliver. Have the simulations that we've been running been entirely conducted on GADI, or have we been utilizing any other HPC systems? So we were using Rygen a lot, which was the predecessor of GADI, but we have also been using some other HPC facilities in Australia, but not to a large degree. Most of what we've been doing has been on Guardian, and that's certainly the machine that we're focusing on moving forward for doing the big large simulation that we want to do, the 8,000 cubed one. Next question is, how sensitive is the simulation of dark matter density to the initial perturbations? So very sensitive is the answer, I think. So it depends on what sense. I mean, you can get kind of sensible results in terms of the development of a cosmic web and things if you, so that kind of filamentary structure that you see, and you can get that reasonably easily without needing very precise initial conditions. But if you want to get things such as the correct clustering of galaxies and dark matter halos, then you do need to be quite precise with the initial conditions. As well, if you don't get them right, you can get spurious structure formation as well in your simulations. And so it's really important to avoid that as well. Another question here, do you write the simulation software completely yourself or use some already existing hydrodynamic codes? We use existing codes, basically. In astronomy, there are a number of codes. We're actually quite good in this respect that the codes are normally open source. And so there's quite a large industry around taking these codes, which are honed by many different researchers over the years, and then adapting them to answer your particular science questions. So you'll get many different versions of codes such as Gadget 2, which exists out there, which people have taken and modified in certain ways. So yeah, it's rare for people to write their own codes. And certainly in Genesis, we are making use of publicly available codes such as Swift, and then adapting them with different physics and things as well in collaboration with the original authors. On the semi-analytic model side of things, because they're so much less computationally intensive, and I guess in that sense you can focus more on the physics, which I guess more our domain as astronomers. People tend to write their own semi-analytic models, and we did it as well for this work. We've got a number of semi-analytic models, actually 3 or 4, which have been written by members of the Australian community over the years to answer various different questions. So in that sense, we do write our own codes. Another question here, have you considered using Parallel X from Louisiana State University for astrophysical simulations? Perhaps this approach can improve performance. Yeah, I'm not not actually aware of the details of parallel X, but I do know there have been codes written over the years using things like Charm++ and other codes which are for distributed computing. And so I don't know if that's similar to parallel X. Yeah, I won't embarrass myself by going any further into that. So I'm not directly aware of that. And do you consider using TPU in simulations in the future? I think there is probably some research ongoing into that. It's not something that I'm personally aware of or that any of my immediate collaborators are involved in. But I can certainly imagine there would be interest in that in the future. I think that's the kind of direction people would be interested in going.
Thank you, Simon. Perhaps I will ask the final question. We have several students. We run a computational engineering course at ICM, and I can see there are some students from our courses. In this large number of new huge-scale facilities, experimental facilities, there surely must be some sort of growth in astrophysics. What are the chances, career chances for young scientists, for computational scientists? Is it a good field to consider for young people?
It's that's an interesting one. So I think things are improving. Yeah, I mean, yeah, yes and no is the answer. Astronomy in general, I think, is a good field. I think it's very collegial. It's I think relative to other fields, it's actually quite small, and many people know each other across the world, and you'll often bump into people at conferences and things, which is really nice. But when it comes to the theory side of things and the simulation side of things, it can be difficult, I would say, to really get traction. And often that's because it requires a lot of code development and software development, which isn't often recognized through the kind of traditional mechanisms of basically publications. And so when you're going for grants and things, people are still, unfortunately, very focused on your publication record. And so if you spent a lot of time writing codes and doing code development, you can't count that towards your publication record in many instances, unfortunately. But I am optimistic that's actually changing, and reasonably quickly, actually, in astronomy at the moment. There's a large number of people who are recognizing this, and particularly high up, which is good because they're the people who can actually affect change. And so I'm hopeful, in coming years that situation will improve.
Thank you, Simon. Thank you on behalf of all listeners, and let me explain or remind you that Simon audio and video is coming across from Melbourne. It's about as the crow flies, so it will be over 20,000 kilometers if you count the length of optical cables. That's a miracle, that we can communicate like that. I think it's brilliant. Of course, God knows which path this packets took to reach us here. But your slides were presented from servers in Poland, where they were pre-loaded earlier. So there was absolutely no problem with the visualization and the animations, which are very beautiful. The whole talk is really fantastic. Thank you so much, Simon. Great pleasure when we all can fly and move. You're most welcome to visit Warsaw. Thank you.
That's very kind. Thank you very much.
Thank you. And let me just remind you, perhaps I will ask my colleagues to show this few slides. So we had the pleasure of having Simon. Our sponsors, as I said, is HPC Wire, Tabor Communications, Atanami, enterprise AI. I welcome you all for the next week's seminar, the same time, Thursday, 4 p.m. Central European Time, and other times wherever people are. And that, again, I believe will be very, very enlightening talk, very fascinating about the domain of quantum computing, different kind, not gate computer, slightly different than what we've heard from Scott Aronson at our first lecture. So I welcome you for this talk. And in 2 weeks' time, we will be listening to Dr. Franciszek Rakowski, our colleague from ICM, who is developing a very sophisticated model for predicting the spread of COVID-19 epidemic in Poland. There has been a lot of developments in this model. Let me remind that the model was created over about 10 years ago, specifically for the spread of flu epidemic. And recently, about 2 months ago or less, we decided to undust it, update it, and bring in all the important features to understand the spread of COVID-19 in Poland. And right now, this model most probably will become an operational model for decision makers in Poland. So with that, I thank you all for your presence, and thank you very much. Goodbye, and see you in a week's time. Bye-bye.